I became an undergraduate in Cambridge in 1960, and at that stage, all the people who taught me really believed that the continents were where they are now and had been there, right, for the whole of geological time. How they quite squared that with erosion and things like that were questions which undergraduates asked, right, but we didn't get a satisfactory answer. It's fair to say that much earlier than that, particularly Wegener had proposed that the continents did move around. The trouble with what he had to say was that he was prepared to use absolutely any sort of data, right or wrong, right, to drive the cause forward. And for instance, the errors in the geodetic measurements between North America and Europe, which suggested that the separation was about 10 meters a year, this was all grist to his mill. And it was this complete mixture of good and bad which made the subject really a total mess, I think, for the first half of this century. And what really changed things was the war, and the fact that a whole load of geologists and people like that went to sea and looked at the bottom of the sea. Not very well at the beginning, but steadily improving. And if I can illustrate this with the first slide, which is one of Arthur Holmes' slides taken from, pictures taken from his book, published in 1944, he had the notion, right, that the continent split up in this way, that there was sort of distributed deformation, the continents foundered down into the mantle, right, and that there was a large region across here in which you formed some sort of new ocean, completely unspecified as to how. And this sort of notion was fairly typical of the ideas that geologists had, right, even when I was an undergraduate. Right, physics was one of those nasty things which they'd been taught as an undergraduate and which they were going to try and avoid. And really what's happened since then is that the subject has become a branch of physics. The beginning of all this, right, the beginning of the change, was a suggestion by Harry Hess. And this was in 1960, and what he did was to propose that the new seafloor was formed not in this distributed way between continents, but along a single line down the middle of the oceans. And the reason why he made this proposal was really because this is where the earthquakes are. Well, at the time he made it, the earthquakes were distributed, the locations weren't very accurate. Right? There was a band of a sort of, 400 kilometers down the middle of the oceans, right, in which there were earthquakes. And he said, no, it's not like that, really. The earthquakes are very localized. The new seafloor is produced right along the line of the middle. And this was a completely revolutionary suggestion. Right? And at the time he made it, really not very soundly based on observations. And this was actually one of the features of both this and of the thing which I think is the most important discovery ever in the earth sciences, which is that of magnetic anomalies. What then happened was that Vine and Matthews, working at Cambridge, proposed that along this line, right, along the line of what's now known as the Mid-Atlantic Ridge, right, where the new seafloor is made, material wells up and it melts and produces basalt. The basalt contains magnetic minerals, iron oxides, and they become magnetized in the present direction of the Earth's magnetic field. That's along here. Now, fortunately for us, the magnetic field reverses. And I'll say a little bit more about that problem at the end. That's still one of the really big, interesting areas, right, of these large-scale enterprises. But the magnetic field does reverse, and it reverses not periodically like the sun does, which would finish us, right, because that would just leave, if the plate separation was constant, that would just leave stripes of reversely and normally magnetized material across the seafloor. It reverses irregularly. And if any of you are interested in signal processing, you'll know, right, that what you really want to recognize something is something which is totally chaotic, because it doesn't repeat, so you can recognize where you are in the time sequence. Well, that's the key to what we can now do. Because if you can establish the reversal timescale, and that's shown here along the bottom, right, here's the present day, going back 1 million, 2 million, 3 million, 4 million years, you can see that the region here is the region where the main field is pointing in the present direction. Then there are regions here with variable lengths where the field pointed in exactly the opposite direction. And all your compasses and all the methods, right, the Boy Scouts use to find out where they are in the woods, all of that wouldn't work because they would go south and all the maps would have to be changed. These periods, right, are irregular, as I say, and they lead, and they're just the right sort of time scale between the reversals to produce stripes on the magnetic of reversely and normally magnetized material on the seafloor, which we can then recognize simply by towing a magnetometer across the surface, at the surface of the sea, right, and get profiles like this. And then you can match those profiles up with here. This is this was done a long time ago now, right? This is the synthetic profile produced from this. You have to be a little bit careful because what you actually measure when you tow the magnetometer is not the three components of the magnetic field, but simply some scalar thing, and you have to actually calculate that, and that's not a trivial thing to do, and various people, all my students, always now get that wrong. Now, the key to this, if it was right, and it was proposed really to explain the fact that a classified military survey done off the west coast of California had found these stripes. The problem with this survey was that because it was classified, right, we didn't know what the seafloor looked like in the area where these stripes were, and we didn't realize that there was a spreading ridge producing new seafloor just off the Californian coast. And this was really held the subject back for quite a bit because we didn't realize what we were looking at. But if this idea works, right, then you can do all kinds of things. The first thing you can do, right, let me first of all show you what the technology, improvement in technology, which makes most of these ideas now rather obvious. These are earthquake locations now in the Atlantic, right? And the network which is used to locate these earthquakes is a network worldwide of seismometers, and it was installed in order to detect nuclear tests, underground nuclear tests. And there is this connection between the military and the scientists which runs through the whole of this subject. We're working on Earth, right? These things have strategic importance. And the military has been a major funding for most of the developments in the technology and finding out where these earthquakes are. And you can see that once you had this, if Harry Hess had had this picture, there really wouldn't have been any doubt in his mind, right, that this is the location, right, of where new seafloor is being formed. And you can see something rather nice here, which is that the seafloor, the ridge, is exactly midway between the continents on either side. Right? And that's simply because the ridge produces material on either side at exactly the same rate in almost all parts of the world. And one of the curious things is that even now, we don't properly understand why that should be. The other thing which we can now do, again with a development of military technology, is map the seafloor in great detail. This is a bit of the Pacific, right, with the spreading ridge coming down here. The scale here, that's about 100 kilometers, and you can see the extraordinary detail we now have of the seafloor. Here is the spreading ridge, lots of little volcanoes with craters in the top, nice linear stripes here of seafloor which was produced here, some really rather complicated things here which are only just now being worked out, but the detail is extraordinary. And this is mapped, right, with sound because electromagnetic radiation won't go through the seafloor, and it's mapped essentially by just going backwards and forwards and putting these strips together, right, on a computer and then producing this artificial color in illumination. And this really now makes many of the things which were so controversial when they were first proposed 30 years ago really obvious to anyone. And it's this terrific change in the technology which actually, though it hasn't been much emphasized this morning, underlies essentially all that we're doing. Right? It becomes easy to do things which for the previous generation was impossible. And this is really one of the wonderful things about science. I'm sure if I live long enough, I will come here and hear people standing behind this stage telling me really how simple all the things which I now don't understand are. Now we've got the technology to see them. So that was really where we were. Now, one of the very early surveys was this survey here of the Northern Atlantic. And as a sort of comment on this, this now is colored to show the symmetry. Here's the spreading ridge. Here's the reversals. Right? Here's the reversal timescale, now going back to 10 million years. Astonishingly, this picture was published without any comment on the symmetry about the axis. Right? It came to Drummond Matthews to review, right? And he immediately noticed the symmetry, and he wrote back to the journal saying, wasn't this a beautiful confirmation of his and Fred's ideas? Right? He got, for his pains, right, a paragraph added to the end of the paper saying that all his ideas were nonsense and this didn't in any way support what he'd said. Within a year of that happening, of course, the apple cart was turned over, the bandwagon started to roll, right, and the same people were claiming that they had discovered it, right, and such is the way of things. Now, that was the beginning. This is one of the most famous of the early profiles. This is the so-called Eltanin 19 profile. We call these, all these things are called after the ships. It was the Eltanin which took this. It was its 19th cruise. And the observation is the top one, and the model is the bottom one. We can now do rather better. Right? Some of all these things are just because the modeling wasn't very carefully done right at the beginning. This actually, the fact that the high is here rather than on this side is due to the fact that the magnetic field of the Earth isn't exactly a dipole field. Right? And if you take that into account, everything fits together. Well, this really is the fundamental sort of underpinning of my talk, which is that here we see physics in the form of magnetism, right, coming straight into the earth sciences to give us a sort of precision and accuracy, right, which was completely undreamt of by the early geologists. Right? And, of course, once you can do this, you can recognize these magnetic reversals here in the oceans. You can recognize them in sedimentary sequences. You can recognize them in basalts on the continents. And you can date all these things and start to tie everything down. And that's now, I mean, one gets now very excited about changes, right, of the order of 500,000 years or so, which at that time was not the case. Now, we can also use those ideas to map the whole of the oceans. And here is a map, not, I'm afraid, quite up to date, but showing the whole structure of the oceans. And suddenly, using these magnetic anomalies, we could map and date that half of the Earth's surface which was proper ocean. Not things like the North Sea, and I'll come back to that in a second, but the part which is floored by basalt. All these oceans are produced along mid-ocean ridges. You can reconstruct the whole evolution of the oceans, you work out exactly what's going on, and so on. And we all had an absolute field day doing this because, of course, there was a huge amount of data sitting in data banks. The computers were getting faster, and within about 10 years, right, we had basically worked out the whole of the history of the ocean basins, and furthermore, we had drilled them to check, right, that things were possible. And the drilling is another story. The drilling started with a project to drill through the oceanic crust into the mantle below. That went foul of essentially Johnson's re-election campaign. Brown and Root, who were the main contractors, illegally gave $10,000 to Johnson's re-election campaign, and that sunk the whole project. Scientists were not really very sophisticated, right, at that stage. I very much doubt that sort of thing would happen now. A nice twist to that story is that the platform, which was designed to drill through to the crust mantle boundary through the basaltic layer is now the standard platform which we use all over the North Sea to drill and produce our oil. Unchanged, I may say, right? Exactly that one. They're the semi-submersible rigs. It's simply where that came from. And there is always this interaction in this subject between these ideas, which start off as very academic, and very, very quickly become of major commercial importance. Now, let me now say a little bit about where we are now in terms of actually measuring these motions. Obviously, right, the way one would think of measuring motions is not by all this rather complicated business of using the seafloor as a tape recorder, but actually saying, you know, let's put a tape measure out and see how fast things are moving. Right. Well, in fact, that has turned out to be quite difficult because the motions aren't very fast. I mean, the fastest motions that we know about at the moment are only 25 centimeters a year, and they're underwater. Right? And you can only really work on land. Right? And so you have to work with motions which are really rather small, and it took space techniques, really, before we were able to measure these directly. And this picture here is of Lagios, which is a satellite, and it looks rather pretty because it's completely covered by corner cube reflectors. And the object of these, it's made out of tungsten, it's a heavy satellite. The object of these corner cubes is that you can shine a laser beam, exactly like the one I'm now pointing at it, and that is reflected straight back to where I'm standing. No matter, because they're corner cubes, no matter where I'm standing, it gets reflected straight back. So what you do is you simply measure the time of flight from your telescope, right, point it at the satellite and measure the time of flight to and from the satellite. And then the idea is really rather simple, which is if you have a satellite passing like this, right, and you do that from 2 stations, you can use the fact, right, that you've got timing and all the rest to reconstruct the position of the 2 stations. And when you do that, you can measure the motions to a few millimeters. The distance is to a few millimeters. You do that several times, and then you can measure the displacements. And when you do that, here is a picture. Now, the satellite measurements here are shown, right, by these green error ellipses and the arrows, right? And these are principally from Dave Smith at Goddard and his co-workers, right? And here is a whole series of these arrows. This vector here is from geology. Right? This is Richard Gordon's best estimate of what the velocities and the directions are for these various points on different planes. And what you can see, I think, is the astonishingly good agreement between the direct measurements now, right, and these geological measurements, right, both in magnitude and in direction. Now, the agreement you can look at in a different way. You can plot the rate measured right here along this axis by the geodetic means against, this is Richard Gordon's, this is an earlier one, the rate from geology. And what you can see here, right, these are the best fitting lines, right? And if everything's all right, they should go through the origin and they should go at 45 degrees to this axis because both rates were the same. And you can see that there is a small discrepancy. Right? The geological rates are actually a little bit faster, right, than the geodetic rates. And I didn't think a very great deal about this. Right? I thought the difference here of a new one is only 4%. And I thought, well, you know, there's a scatter of points, right? And this is, after all, geology. I shouldn't fuss too much. I was wrong. The error is real, right? And it's caused by a difficulty in calibrating the geological timescale to the radioactive timescale. And probably it's the radioactive decay constants which are wrong. We know this because of the fact, and this has only just come out in the last week, that you can actually measure, you could get the geological rates also from celestial mechanics and the correlation with the ice ages. Right? And by using the Milankovitch hypothesis, Nick Shackleton and various other people have recalibrated the reversal timescale, and it's done 2 things. right, the discrepancy is now only 1.5%, and that really I don't think I believe. The other thing it's done is to make the rates, the spreading rates, constant. They were variable, which I didn't believe, because the time constants of the whole process are really very long, right? And I didn't believe that you could vary the plate motions on a short time scale. Well, nor you can, right? If you do it all properly, that's what happens. So this is really quite astonishing, I think, right, that one can do this well. Now, we next say a little bit about the continents. I carefully avoided talking about the continents, and I'm not going to say very much about them, other than to say that obviously when you look at earthquake locations on the continents, right, and here is one's for the Aegean, right, you can see the coastlines. Here's the Black Sea in the north, right, this is Greece, right, here's Cyprus, Israel over here. You can see that the earthquakes are distributed. This is not due to errors in the locations. Right? We know the locations of earthquakes on the continents very accurately because they break faults. Right? And some of those breaks are really very spectacular. Here is one in Greece. You can see this is about 30 meters high. These scratches down this surface are produced by repeated earthquakes on the same fault. Right? And they can see how regular the whole thing is. It's just drawn down like this. If you look at other ones, this is a more recent break. This is actually in the northwestern part of the US. From an aeroplane, here's a little river valley. This step here is about 2 meters. Right? So, you know, not only can we locate where these earthquakes are, but we can actually see everything all being broken up. So there really isn't any doubt. Now that caused us, right, to worry, right, whether we could use these same ideas on the continents. You're clearly going to have to be more sophisticated. It's harder, right? And what you want is a theory which allows the motion to be distributed rather than concentrated on a single line. I had a go at this very early on, and this is a picture I drew in 1970, which was published in Nature, right? And essentially the idea is that there are lots of small blocks which are moving in various different directions. Well, once again, we can now do this geodetically. Here is now again from Dave Smith, looking at what the motions are, right? And you can see the pattern is exactly the pattern that we got from the earthquakes, right? The error ellipses still encompass the velocities that we get from the earthquakes. If I was involved in this affair, I'd now be really extremely disappointed, right? Because the first order observations, right, have simply confirmed what we knew from the earthquakes. I think the next round is going to be much more interesting, but it's going to be much harder because you need an awful lot of points to add much to this. Now, let me say just a little bit about what came from that work in the Aegean, which is the idea that in continents, rather than the extension being localized on single faults like down the middle of the Atlantic, the earthquakes are distributed, the whole of the continental lithosphere is being deformed. And this is what we think has happened in the North Sea. And this picture I show simply to show you what actually doing geophysical experiments looked like, right? This, by the way, is Drummond Matthews, right? This is about a ton of high explosive. And what he is doing, right, with Phil Christie is, and this is the fuse, right? And what they're doing is waiting for their 20-minute gap, right, which they negotiated with all the oil companies all over the North Sea, because, of course, if you let off that amount of explosive underwater, you kill divers within a very large range. Right? This is not desirable. Right? So here they are, they're planned, and they're waiting for it to go. And what we wanted to do was simply to see whether the structure of the North Sea was what one would expect from a very simple stretching model. And the idea is simple, right, which is that instead of the extension being localized, let's say along here, that the whole of some piece of the plate gets stretched like this. The continental crust sitting on top has got a different composition from the mantle underneath, and when you stretch, it's thinned. So simply by measuring, right, the crustal thickness, you get a reflection of sound. We do everything with sound off this boundary here. You ought to be able to tell whether this is what happened. We did that, right? Forward a bit. Out of sequence. Oh, got very out of sequence. I beg your pardon. I'm going to have to go back. We did that in the North Sea, and we found the result, right, that you would expect, right, from this idea, which is that the crust beneath the center of the North Sea has been thinned, right, from what it is beneath our feet here, which is about 33 kilometers, to something like 50, so by a factor of 2. And what then happens is, because when you stretch, this material down here stays at constant temperature during the stretching, the temperature structure, right, changes. And the temperature gradient in the crust and in the upper mantle increases by the same amount of the stretching. And then the whole thing cools back to what it was there, and the cooling is associated with thermal contraction and hence with sinking. This is essentially why there's a hole in the middle of the North Sea, right? It's contracted, and the reason why we can all, in this country, live off the proceeds of the oil is because it got cooked by this gradient. And all oil companies now essentially use this idea, right, in all their calculations, right, as to oil reserves in the basins around continents. Right? And this is extraordinary speed now with which these ideas get applied. Unfortunately for us, right, of course, once they can do it, they're no longer interested in supporting research on finding out more about it, because they think they know everything. Right? So that is our undoing, right? The oil companies, particularly the British oil companies, like BP, are now being far too successful for my liking in finding oil, right? And what they want to know now is how to get it out, not how to find it. The other thing you can do, right, with this, which I show here as a cover of Nature, which is an astonishing feat of technology. This is the surface break of the Landers earthquake in California, and these are essentially interference fringes, right, generated from a satellite in orbit around the Earth, ERS-1, right, of what these motions were. And these are essentially just like any other sort of interference fringes, right, and allow you to map the displacement. Now, this is going to be terrific, because you don't have, or you can do it worldwide, you can put these satellites up, you can map the continents, right, and then when there's an earthquake, even if it's not in an inhabited area, you can then look and see what the motions were. And this, I think, is going to be a complete change in technology, the latest one. Now, I said I'd say at the end a little bit about the magnetic field, and here I'm going to play a video. I can start the video. What I'm going to show you, right, is what I think is another real triumph, right, which is that Dave Gubbins and his various students and associates have been able to reconstruct the form of the Earth's magnetic field back into the 18th century, right, actually right back into just the 17th century. And what I'm going to show you, which is actually playing up here, right, is the form that the changes in the field take, but not at the Earth's surface, but at the core mantle boundary. Right? And the thing I particularly want you to notice, right, is that here are big flux concentrations, right, round the Pacific. Right? In the Pacific, the field changes rather little. Right? In the rest of the world, the field changes radically. Right? Now, if I can go over onto these things, it still works. There's one on each side, I think, starting now in the 17th century. Watch the movement, right, in the middle here and in the Pacific. In the middle here, right, between, you can see the continental outlines and the Pacific. And what you'll see is that some of these features run rather rapidly across this region here. Will develop, I hope. Seems as if it's stationary to me. developing. Yes. Yeah, it's no, it's repeats. It's 4 repeats. Anyway, if you look at this area here, right, in the middle, you'll see it develops quite quickly. Here we go. Right, I can see it now coming. Watch this area here, this grows. Okay. Here it grows really quite quickly. There you can see contours changing, a new contour starting, right, a region of blue developing, which then moves westward across here to South Africa. And what these are flux loops, right, of field which are being expelled from the core, right, in this area. Changes rapidly in this area, but the Pacific changes very little. Right. We'll all repeat in a minute. Right. You can see how different it is now. Here is the top one of these is the, which way around is it? One is the 18th century, the top is 1715, and the bottom one is 1980. Right. Now, the reason why one can do this is because of measurements of the magnetic field by people like Cook, right, who sailed over the Southern Oceans. And with modern inverse theory, you can actually convert these measurements down to the field of the core. And it's this use of computers on very old data which has allowed us to see the time development of the field in a way which is entirely unexpected, right? And it's really one of the real big surprises, I think, that you can do this. And what this has done is to give us some idea as to how the reversals might happen. And thank you. Here is the present field system. Right? And these slides are also from Dave Gubbins, right, at Leeds, showing, right, the field in the north and the south, concentrated in these field, in these flux concentrations. And if you look at the field on the core mantle boundary, it doesn't look like a dipole at all, right? The reason why it looks like a dipole at the surface is simply that all the complications disappear, right? Because here we're 3,000 kilometers below our feet, right? So that's why we have a dipole field. It's simply the one that disappears least. But in fact, you have these rather complicated, this is a real three-dimensional calculation, and what I'm going to show you, right, is a series of pictures of how these flux loops move during an oscillation of essentially the magnetic field. Now, this isn't the real thing yet, but it does show you how this system can reverse, right? And what to watch for is these loops here, these flux concentrations here, grow, these ones decay, and these ones essentially replace those ones. So if I go through it, you'll see them moving northwards, a new set starting up, these ones decaying, right, these growing, right, until, here we go, finally, right, one more, and we're back to where we were at the beginning, but with the opposite field polarity. So some of the numerical models we now use on computers that we're now playing with actually behave in the way that we see the Earth to behave. But this is still a periodic reversal rather than an irregular one, right? And we really want this thing, right, not to reverse periodically, but to reverse irregularly. So really what has happened in my working life is that the geology has gone from being a subject where people wave their arms, right, to something, right, where if you choose the right problem, and this is one, I could also have talked about the work on the Milankovitch hypothesis, which is really now having a big impact on climatology and is getting equally precise. And it's first of all, the use of methods from physics and chemistry, then actually the application of the same sort of determined precision, right, to these problems as has always been the case in the more quantitative sciences. And the fascinating thing is how much you can now do. And the Earth that we're now standing on really isn't very like I mean, we don't think of it in at all the same way as we did right when I was an undergraduate. Thank you.